Hello everyone, in this video we are going to discuss race condition in process synchronization along with an example code, and also we'll discuss semaphore and implementation of semaphore. So to begin with, cooperating processes. Cooperating processes are a set of related processes that are working on tasks while sharing a common data. For example, reservation and cancellation process in a ticketing system. The reservation process, it reserves a seat and decrements the ticket count. Cancellation process, it cancels a seat and increments the ticket count. So here, reservation and cancellation process, they are related processes, cooperating processes working on a common data called ticket. They both are updating the ticket count. So hence the reservation process execution will affect the cancellation process execution. Cancellation process execution affects the reservation processes. So reservation and cancellation process are hence called cooperating processes. Some other examples include withdrawal and deposit processes in a banking application, the buyer and the seller process in an e-commerce application, and so on. So the problem with the cooperating process is concurrent access to the shared data by the cooperating process may result in data inconsistency. Let's take an example and understand. Here we have a producer process which produces an item and increments the item count. So the counter here is item count. A consumer process consumes an item and it decrements the item count. So the counter here is a shared variable between the producer and the consumer process. The counter plus plus and counter minus minus here are a high level instruction. Now when they are compiled into low level instruction, each instruction is a set of a low level instruction. So here for example, counter plus plus is a set of these three low level instructions. The counter is first stored in CPU register 1, then the CPU register 1 is incremented, and then the register 1 is stored back in the counter. Similarly, counter minus minus is the counter value is stored in register 2, the register 2 is decremented, and then the updated register 2 value is stored back in the counter. Now, concurrent access, that is interleaved execution of CPU between these two processes may result in data inconsistency. It means when the producer is executing these three set of codes, and in the middle the CPU switches to execute the consumer code, then this data will not be updated completely, and hence it might result in a inconsistency. It might result in improper data. So when the process is executing in middle, if the CPU switches to other processes, the data will not be completely updated. That's the data inconsistency issue. Now let's take an example. Consider that the initial count value is 5. Now say at time 0, the producer process executes. So the first instruction, counter is stored in register 1. So now the register 1 value is 5. Now say again the producer executes its second instruction. The register 1 value is incremented, hence register 1 value is 6. Now next time the CPU switches from producer to consumer code. So the first instruction of the consumer code executes where the counter is stored in register 2. The counter value is 5. So it is stored in register 2. Register 2 value is now 5. Next time instant, the consumer code continues to execute its second instruction, which is register 2 is equals to register 2 minus 1. So the register 2 is now decremented and its register 2 value becomes 4. Now the CPU switches to execute the producer code. So the third instruction of producer, register 1 is assigned to counter, hence the counter value will become 6. Here register 1 value was 6, isn't it? So that is assigned to the counter, and the counter value becomes 6. Now the CPU switches to execute the last instruction of the consumer code. So register 2 value is assigned to counter. The register 2 value here you can see it's 4. So the counter value will now become 4. Now the initial count was 5. There was one item produced and one item consumed. So the final result should have been 5. But here we see it is 4, which is not correct. If the last two instructions are exchanged, then we can see that the final result would have been 6. So we see that the result, the final output what we are getting is not correct. We should have got 5, but we are either getting 4 or getting 6. So in order to, this is called as a race condition. So here's the definition of race condition. When two or more processes attempt to modify a shared variable, then the outcome depends on the order in which the access takes place and may be incorrect. So when two or more processes are accessing a shared variable, then the outcome It depends on the order in which the processes access the data, and it might be incorrect. So here we have seen if it might be 4 or it might be 6. Now, in order to avoid this, what should happen is, for all these 3 instructions should be executed incomplete, and then the consumer instructions should be executed. That is, we need some orderly execution among the processes. The producer code should be executed, then consumer code, or else the consumer code should execute full and then the producer code should execute. So that's what. Maintaining data inconsistency requires mechanisms to ensure orderly execution of the cooperating processes. So this is all about process synchronization and coordination among the processes. So this race condition may occur between threads, that is when threads share a common data, or it may occur between a parent and a child processes. So when they update a common data. Now let us look at example code. So here we have we are creating a child process. So in this program we are creating a child process by calling fork. Okay, and here you can see the child process is executing a function called char at a time, and it is passing a string output from a child. The parent process is also calling the same function char at a time, and it is passing output from a parent as a string to that function. Now look at this function. What is this function doing? It is receiving the string as an argument and setbuff stdout null. Stdout is standard output, which is nothing but our terminal or a monitor. So we are flushing out everything from the monitor first, and then using a for loop, this for loop pointer is pointing to the string, and we are printing one character at a time using putc function. Putc is a unformatted output function. So in this for loop we are printing one character at a time to the stdout. Stdout is our terminal. So what is this function doing? Basically it is writing one character at a time to stdout, that is our terminal. So here both parent and child, they are calling the same function, that is both parent and child is writing one character at a time to the standard output. So here you can see the standard output is shared between the parent and the child. So when I execute this, you can see here the output, it is not correct. It should have been output from child followed by output from parent. So what happened here? The O from the parent was printed, and then the child executed, and then the parent executed. There was a context switch here, hence the output is not proper. So this is example of a race condition. Let me execute again. So you can see now it is executing properly, because it happened that the parent executed completely and then the child execute. So sometimes it will be correct, sometimes it won't be correct. So now you can see here the output is not correct. So here what's happening, parent and child, they both are trying to write to the standard output or a terminal, and as there is no synchronization among the parent and child, we see the output is not proper. So same thing can be seen in case of threads also. So what I've done is I have created here threads. You can see producer and thread, consumer thread. The producer thread, it is passing thread 1 as an argument, and the consumer thread, it's passing thread 2 as an argument, and it's the same function that I have used. The producer process is also writing one character at a time to the screen, the same function that I have explained with respect to the parent and child, right? So it's the same code I have copied in the producer and the consumer function. So basically these threads are writing one character at a time to the screen. So now when I execute this, you can see here, is this output correct? It's not correct. Why is that happening? So you can see here when the thread 1 was executed till this time, and then there was a context switch. Then the consumer thread executed. So the output is not correct. That is what is the race condition all about. Now how to avoid this, we have to ensure some orderly execution. So for that we have a synchronization tool called as a semaphores. Semaphores are synchronization tool. So what are basically semaphore? Semaphores is it's basically an integer variable, and this integer variable can be accessed by only two functions, atomic operations. Atomic means it will execute completely or it will not execute. There will be no context switch when these functions are executed. So semaphore, it's a synchronization tool, it's an integer variable. It can be accessed by only two operations, wait and signal. This wait operation is also known as P, and the signal operation is also called as V, theoretically. Okay, so what is this wait and signal function? So this wait function, you can see here, it is taking the semaphore as an argument, and in this wait function it is checking if that semaphore value is less than equal to 0. So the value of semaphore is less than equal to 0 means the resource is not available, hence the process must wait. So if the value of semaphore is less than equal to 0, the process is made to wait in this while loop by doing nothing, by executing this simple semicolon. It is spinning in this while loop. Suppose if that semaphore value is greater than 0, then the value of the semaphore is decremented. Simple to remember. Wait, it makes the process to wait if the semaphore value is less than equal to 0. If the semaphore value is greater than 0, the semaphore value is decremented. What is signal function? Signal function is just increments the semaphore count. How do we use these functions? So before the process tries to use some shared data, it will call wait of S. Okay, so if that shared variable is available, if no other process is using it, then the process will be allowed to move further, and the process will be in its critical section code. That is, it will be allowed to access that shared data, right? If there is some process which is accessing the shared data, then this wait will make the process to wait in this while loop. Okay, and then once the process is done with its critical section, it has to call signal. So wait, it's used in entry section, and signal, it's used in exit section. Now, how to implement this in our programs? Using Semaphore library. Okay, so we have a Semaphore library, semaphore.h. This Semaphore library provides a data type sem_t to declare the semaphores, and we have a sem_init function. It takes 3 arguments: the semaphore, right, and the shared. So this will be 1 if the semaphore is between the processes, and it will be 0 if it is between the threads, middle one. And third one is the value which the semaphore we want to initialize. So the whatever value we want to semaphore to be initialized, right? So that is the third argument. Then sem_wait we have seen just now, right? So this is sem_wait, and sem_post. Here we don't have signal function, but we have semPost. Okay, the signal function is called as a semPost. And finally, to destroy the semaphores, we use sem_destroy function. So we can use the semaphores using the Semaphore library, by declaring the semaphore, by initializing the semaphore, by calling sem_wait, by using sem_post, which is nothing but signal function, and sem_destroy. So this is how the Semaphore library is. So we discussed race condition, and we saw an example code, and then we discussed what are semaphores and the Semaphore library. So thank you.